Hi, I'm Ryan Baker and this is Big Day in Education. Today we're going to talk about automated feature generation and automated feature selection. Automated feature generation is the creation of new data features in an automated fashion from existing data features. One example is multiplicative interactions. With multiplicative interactions, you have two variables, A and B. You take them, you multiply them together, you get a new variable C. And then, if you're doing automated feature generation, you do this for all possible variables. Multiplicative interactions is a well-known way to create new features, and it's got a rich history in statistics and statistical analysis. It long predates analytics or data mining. A less common variant that you'll sometimes see is A divided by B, and you do that for all possible combinations. Of course, there's one challenge with that you don't get with multiplicative, and that's that you have to decide what to do when B equals 0. And sometimes people will just treat it as missing, sometimes they'll just treat it as 0. Then there's function transformations. X squared, square root of x, the natural log of x. You'll see people doing these things, especially when they think the data is non-normal, which, as we've talked about before, doesn't matter quite as much with data mining most of the time, but can still be useful to think about, especially if you're doing something like, say, linear regression. Another method for automated feature generation is automated threshold selection, where you tune a numerical variable into a binary. What you do here is you try to find the cutoff point that maximizes your dependent variable. J48 actually ends up doing something very much like this. So if you're doing J48, you really don't need to binarize necessarily. But if you're using other algorithms, it might be useful. Now, it turns out that you can hack this in the Excel equation solver, or you can do this using code. Now this raises the question, why would you want to do automated feature generation anyways, when you've got a lot of algorithms like J48 that'll do some aspects of it for you? Well, a lot of algorithms will do some automated feature generation of sorts. But doing some automated feature generation before running a conservative algorithm like linear regression or logistic regression can provide an option that's less conservative than just running a conservative algorithm. But at the same time, which is more conservative than algorithms that look for a broad range of functional forms. The trick is that specific algorithms like J48 will do specific types of transformation or automated feature generation, but they won't do all of them, and you don't get to pick. If you do it yourself, you get to pick what you're doing, and then you can use a conservative algorithm if you want. Also, binarizing numerical variables by finding thresholds and running linear regression, even though it's theoretically the same, similar to J48, it's not going to find the same models as J48. There's a lot of other differences between the approaches. Now I should say, there's another type of automated feature generation, and that's automatically distilling features out of raw or kind of incomprehensible seeming data. This is different than code that just distills well-known data features. This approach actually tries to discover what the feature should be. There's been some work on this in several domains. It hasn't been very useful in EDM yet. Maybe it'll turn out to be very useful in the near future. Who knows? The field is still moving pretty quickly. Now let's move to talk about automated feature selection. Automated feature selection is the process of selecting features prior to running an algorithm. So rather than selecting features within your algorithm, first selecting the features before you even get to it. First, before I talk about this more, let me give you a warning. Doing automated feature selection on your whole dataset prior to building models raises the chance of overfitting and getting better numbers, even if you use cross-validation when building models. Because you're making decisions about what variables to use, which is often considered part of the algorithmic process, before you even get to the algorithm, and you're doing it in the whole dataset. So when you cross-validate, you're only cross-validating part of your process. You're not cross-validating your entire process. You can control for this by doing the standard things, holding out a test set, or obtaining another test set later. It's not necessarily wrong to do this, it's just something you got to keep in mind. One approach for doing this is correlation filtering. With correlation filtering, you throw out variables that are too closely correlated to each other. But the trick is, let's say you have two variables, A and B, and they're correlated at 0.99, or better yet, at 0.85. So you know you want to get rid of one of them. But which one do you throw out? It's an arbitrary decision, and sometimes when you do this, the variables that actually have more construct validity or better fit to the data are the ones that get filtered out. And Mike Pedro has a nice example of the cost of doing this, which is sometimes worse performance on new data. An alternative is fast correlation-based filtering by Yu and Liu. In fast correlation-based filtering, you find the correlation between each pair of features, or some other measure of relatedness. I like correlation personally. And then you sort the features by their correlation to the predicted variable. So before you even look at the correlation between the variables, you're going to say, how well do they fit what you want to predict? Then you take the best feature, in other words, the feature most correlated to the predicted variable, or whatever goodness metric you have. You save the best feature. We're just going to take that variable, we're going to put it aside, we're going to say we're keeping that. No matter what else happens, we're keeping our best feature. Then you're going to take each of the features and look at how highly they correlate to that best feature. Anything that correlates to that best feature above your threshold, you're going to throw it out. Then you take all the features that remain, not the best feature and not the ones that correlate too much to the best feature, and you repeat the process in them. You take the second best feature, and then you throw out everything that correlates too well to that second best feature. This gives you a set of variables that aren't too highly correlated to each other, but are well correlated to the predicted variable, or at least relatively well correlated to the predicted variable. So let's look at an example. Let's say that we have 6 variables, a, b, c, d, e, and f, and they're all predictor variables for a predicted variable. And we have the correlations of each of these to each other and to the predicted variable. So the cutoff we're going to do for too highly correlated to each other, we're going to say is 0.65. It's really arbitrary. People often use 6 or 0.75. Doesn't really matter. You can try a few different ones. But we're going to say right now our magic cutoff is 0.65. First, we're going to find and save the best. That turns out to be b. b is a correlation of the predicted variable of 0.68, which is better than any of the other variables. Then we're going to take the variables that are too correlated, in this case c and d. C and b correlate at 0.8, and c and d correlate at 0.7. None of the other ones are above 0.65. So we're going to take c and d, and they're gone. We're done with them. We're never going to look at them again. We've saved b, we've thrown out c and d. What's the best variable that remains? That turns out to be a, which has a correlation of the predicted variable of 0.65. So we're going to save a. A is part of our final set. Now, are either e or f too well correlated to a? It turns out that f is, so we throw f out. And that leaves e. E is not too well correlated to a or b, and so it's the best one remaining, so we keep it. So our final set is a, b, and e. Now note, this set of features was the best set that wasn't too highly correlated. But one of the eventual features kept was actually the worst feature out of the 6. You can set a minimum goodness for features to keep if you want. In this case, if you look back, you'll notice that f had a correlation of 0.32. Not so shabby, so it's probably worth keeping anyways. But the point is, this procedure is going to take the best set that aren't too highly correlated to each other, which means you're going to keep some that are worse than the ones you throw out. Is that clear? Moving on. Another thing you can do is remove features that could have second-order effects. When you do this, you run your algorithm with each feature alone, so single feature models. So in other words, if you have 50 features, run your algorithm 50 times. And do that with cross-validation turned on. Then you throw out all variables that are equal to or worse than chance in a single feature model. This reduces the scope for overfitting, but it also reduces the potential for finding genuine second-order effects. So this is a conservative choice that may lead to less overfitting, but may actually lead to less positive true fitting. Another thing you can do is introduce an outer loop forward selection procedure outside your algorithm. So in other words, try running your algorithm on every variable individually, again using cross-validation. Take the best model, keep that variable. That variable is in the save set, just like before with FCBF. Then try running your algorithm using that variable, and in addition, each other variable. So you take that save variable, you include that, and you include each of the other variables as well, one at a time. So you're going to run a lot of 2-variable models. Then you take the best model and you keep both those variables. And you repeat until there's no variable that's added that makes the model better under cross-validation. This approach finds the best set of variables rather than finding the goodness of the best model selected out of the whole data set. It improves performance on the current data set. It's almost guaranteed to do that. E.g., it's overfitting. It can lead to overestimation of model goodness. But you still may want to do it, because it may lead to better performance on a hell.test set than a model built using all variables. And that's because, by definition, it's also going to produce a simpler, more parsimonious model. So even though it's improving performance on the current dataset, it's also becoming more parsimonious. You put those together, and it's not clear which one's going to win out. They may cancel each other out. You may end up with a better model on new test data. You may end up with a worse one. It's worth trying and seeing how it does. Now you may be asking, why do automated feature selection? Why not let your fancy, awesome algorithm pick the variables for you? Why not let RapidMiner or Weka or SAS Enterprise Miner do its job? The reason is because feature selection methods are a way of making your overall process more conservative. And this is valuable when you genuinely want to underfit. So, to sum up, automated feature generation and selection are ways to adjust the degree of conservatism of your overall approach. Automated feature generation can make a conservative approach a little more liberal. Automated feature selection can make a liberal approach a little more conservative. Use them together and you can play with the space a little bit. These can be useful things to try at the margins. It's not going to turn junk into a beautiful model. If you have junk, none of this stuff is going to really fix it. What you really want to do is do feature engineering. But if you've got a basically decent model, maybe this can make it a little bit better. So, thank you very much for coming to this lecture on automated feature generation and selection. In the next lesson, we're going to talk about a very controversial topic, or at least I think it's controversial, which is knowledge engineering. Knowledge engineering can be really great, it can be really terrible, and in the next lecture we'll talk about when it's each of these things and how to make it great. So thank you very much. I'm Ryan Baker, this is Big Day in Education. Have a great day.